We've got one talk and the talk today is presented by the doctor, where we can see in the fellowship. Influence dissipation and transport, the edge of West. Very interesting. Go ahead.
Thank you. Thank you all for coming, and thank you for the committee to invite me to give this presentation. I haven't come for the festival for a few years now, so it's a pleasure to be there again today. So I will speak about divertor dissipation in West. It will not be only about West, of course, and there will be a bit of transport, but not so much, actually, but more. All right. Okay, so a brief introduction. Okay, we need to control exhaust fluxes in fusion devices. Fulvio explained it this morning. I will read it with my own word. So the confined plasma is hot, 1 to 10 kV, maybe 20 kV, and it interacts with the plasma boundary, which is here in red, with feed lines touching the walls. And in this boundary plasma, the temperature is much lower, 1 to 100 EV. Okay, and it's very thin. Like the interaction between the two takes place over 1 to 10 millimeters. It's a very thin layer. And so we have this very thin layer and strong gradient there because there are transport barriers. It was explained this morning as well. Now you should just think about how much efficient is this transport barrier. If you make the calculation of the heat transfer coefficient, it's about 1 watt per meter per Kelvin. It's better than the walls of this room. Even so, you confine a 1 million degree plasma. And of course, as it was explained, there are several regimes: low confinement mode, high confinement modes. And so, over this very thin layer, you get tremendous flux of power and particle arriving to the wall. And either you will get about 100 megawatts crossing this boundary layer and eventually falling on the wall. If you don't mitigate them, you get parallel heat fluxes along feed lines in the range of 100 to 1,000 megawatts per square meter. You burn everything. Even if you try to cool the components, they will burn. So you need to shape the component, you need to shape accurately the feed lines to spread this power geometrically. The shape counts. And of course, people came with dedicated extraction modules. I would say here the divertor, something specific to extract heat and particles in a specific area. This is meant to control the particle pumping and the particle density inside the plasma. It is meant to radiate the power by, so dissipate the power by radiation, say, charge exchange, recombination. You have, again, several regimes, as I will describe. And at the end, eventually, you need to control the wall erosion, because if you erode the wall, the atoms you remove from the wall will dilute in the plasma, radiate, change confinement performance. Okay. So, basic thing on shape. So this is the standard configuration of a tokamak. We have a toroidal closure of the feed line. We have toroidal confinement. Perpendicular confinement is just carried by a downward motion of the particles with this magnetic field. And so the first, let's say, geometry of the plasma within this chamber were called a limiter geometry. So you just have a wall element sitting somewhere, and the nested flux surfaces surrounding the core eventually touch a part of the wall, and that defines the boundary of the plasma. And you get there, for instance, when you start a plasma in a tokamak. You start a circular plasma, it grows in size. It is circular, like this, and limited somewhere. And then to control better those performances, people came out with the idea of diverting the plasma on the boundary. So you add a coil somewhere and you create this fixed point, or where the colloidal magnetic field is null. And this allows to deport the plasma wall interaction area from the core plasma. And with this configuration, we should improve confinement, high mode appearance, high confinement mode appearance, and so on. Okay. So you just have to remember that there is always a solid component eventually intercepting the plasma, okay, because it makes the plasma jump. And as I said, if you bombard the wall with hot ions or energetic ions, they will erode. Eventually, some impurities will then contaminate the plasma. This we want to prevent. So the idea of divertor is very old. In fact, it comes from a stellarator concept of Spitzer in the 58. This, you imagine here the plasma column confined with magnetic field, okay, like you get an accelerator, and you have the idea of deporting the plasma at the boundary in specific boxes with magnetic field. So that was the concept of divertor. Doesn't work so well because you disturb a lot the magnetic field close to the confined plasma. But eventually, this configuration was optimized to make a toroidally symmetric divertor, and the first concept of it was tested in Germany, in ASDEX, in the 80s, where they get H mode and so on. It was the path to improved confinement. Now, of course, the early tokamaks and early accelerators, they were operated with metal walls. And in fact, the confinement was degraded by metal ions radiating the core. You could not get stable plasma. So people moved to carbon. It opened completely its confinement performances because low-Z materials, when they get fully ionized and enter the plasma, they get fully stripped. There is no line radiation. Radiation is only at the edge, so you get good confinement performances. You even get dissipation of power reaching the wall by the carbon. So there was a big jump in tokamak performances. And eventually, people realized carbon is still not good for fusion because it's a sponge for tritium. It erodes very quickly as well. So you move carbon all around. People said for reactor, we need to get rid of carbon. So we come back to heavy metals. And now tungsten is, let's say, the element of reference for ITER and other concepts. So what's the problem with tungsten? So tungsten is, as I said, it's a reference material because it has a very high melting temperature, about 3,500 degrees. And the erosion rate is low because it is a very heavy material. And so deuterium arriving and striking the material has very low probability to remove one of these heavy atoms from the surface. But is it low enough? In fact, not really. Okay? You have here experimental measurements of the probability to erode one tungsten atom from the surface from the plasma arriving on it, function of the temperature of the plasma. Okay, so what you see, so you have experimental points from ASDEX and JET and WEST as well, and some theoretical predictions from a sputtering theory. So for tungsten, the good point is that the sputtering yield is, let's say, maximum around 10 to minus 2, 10 to minus 3, low, but still too high, and it decreases strongly with temperature. At low temperature, you have a threshold effect due to the binding energy of the atoms in the material. And so what we see both in theory and experiments that you can drastically reduce this probability to erode one particle, per incident particle, if you go to very low temperature. Now, the result of having tungsten eroded and migrating in the plasma is illustrated in this figure where I show database, let's say, statistics on the West experiments, where I show a function of the input power. So we put power in our plasma with radio frequency heating, and I show the radiated power integrated over the plasma volume. The red points are the radiation level at the plasma edge, that's in the divertor, radiated between 10 and 20% of the power. This is what you get in a carbon machine, say, because we still get low Z impurities from the wall, oxygen, carbon, boron. And you see in blue here, what you don't get in a carbon device is this 50% radiated power coming from the core due to tungsten contamination. This is what prevents West to achieve high confinement mode. For instance, there is not enough power creating the separatrix, maintaining H mode. And one specific point I show here is this, we see this low sputtering yield from West experiment at a few EV of temperature of the particles striking the divertor. And this scenario shows reduced core radiation and increased edge radiation, because we have to increase the radiation at the edge to cool the plasma at the edge. So it opens the operational space as a regime of operation, and we are progressing on it. So the consensus for tungsten is that we should keep the plasma touching the divertor below 5 eV to avoid erosion. So the target of dissipating in the divertor is to reduce this temperature below 5 eV. So how do we do that? So I will do a very simple divertor physics explanation with 2 points. Okay, so I will relate what we call the upstream position okay, which is somewhere at the separatrix, close to the confined plasma in the scrape-off layer. And if you follow feed lines down to the divertor, you arrive at the target. So you have power crossing the separatrix, let's say 100 megawatts in ether, for instance. It is meant by goes through this turbulent transport, we would say generally. And then the heat flows along field line in a narrow channel, the boundary plasma called lambda Q, which is a few millimeters. This power goes down mostly by collisions, by electrons. Collisional transport, at least we will assume it, okay? So the parallel heat flow is carried by the gradient of temperature times the collisional transport coefficient. And if you make the math out of it, you find it reduces to a simple expression function of the gradient of the temperature to the power 7 half. The density has disappeared here because of this expression. So to carry this parallel power to the target, you need the temperature gradient. So the temperature is lower at the target than upstream, naturally. And in fact, you find also that because the heat flux goes with temperature at the power 2/7, you find that the temperature is in fact weakly dependent on the power you have to carry. So it's always about 100 dV, let's say, at the separatrix, as an order of magnitude. Now this flux arrives in the divertor and reaches the target. But in the target, particles cross the bisheath and reach the target. There is no collision there to carry the heat towards the target. It's a pure kinetic transport. So you can write that the heat flux is a product of the particle flux times the temperature times the kinetic correction gamma, that is 5 to 10. So you can link the two then and do the math of what's going on. Now what I want to say is that ions reaching the target gets neutralized in the material and re-emitted as neutrals. So ions arriving here with certain temperature deposit the heat in the target and are re-emitted as cold neutrals, and they re-ionize locally in the divertor. This costs energy by radiation and ionization, so it helps to reduce the heat flux to the target, but it helps also to increase the density locally. And if you increase the density at a given heat flux, you have to reduce the temperature. You can also see it because the pressure is conserved along field line for monetary hydrodynamic stability. So if you increase the density locally, you will decrease the temperature accordingly. Then you have to add photon radiation and charge exchange. This will reduce even further the temperature of the plasma locally. So increase the density and try to increase the radiation will help reduce the temperature. Now, what we find is that there are in fact several physics mechanisms that will show that this way, the path to drop the temperature locally will face bifurcations. It's not a continuous path to cold plasma. Sometimes we see bifurcations. So I will illustrate it with some models. So you can find here references to initial models about this bifurcation by Lipschutz, 87, Philip Gendry, 94. Ulrich wrote more recently about exponent radiator regime. I will describe. So first way to understand how a bifurcation could happen in the divertor is the following. So we have power conducted by electrons toward the target, and imagine that it has to be balanced with a certain amount of radiation. So how much goes to the target is simply how much is conducted minus how much is radiated. And this is greater than 0. At least it cannot go negative for stability. And the situation where everything is radiated is called fully dissipative state of the divertor. Now, if you look into how radiation happens, it's mostly due to impurity, the presence of non-fully ionized impurity in the divertor. We will emit atomic lines. Radiation can be quite strong, but most of this atomic line radiation, in fact, peaks around a certain temperature. So the black curve here shows the power radiated by a certain plasma composed of deuterium, electron, and impurity. And I'm showing here the black curve shows the radiated power function of the temperature of this plasma. You see it peaks. Let's say for nitrogen, it's around 15 eV. It's strongly peaked like this, and it decays rapidly towards 0 at high temperature because you get fully stripped ions. They don't emit atomic lines. In the same graph, assuming that the upstream temperature is 100 eV, the red curve shows the conducted power to the target. So if the target temperature is hot, let's say 80 eV, the gradient from target to extreme is small, and the conduction is the temperature gradient, so the heat conduction is small, and it increases up to a certain value when the target is cold. So if you are in a regime, let's say at 50 eV, the conducted power is above the radiation, so you still get power reaching the target. We want to reduce this power, so we will try to reduce the temperature to push this point toward the peak. And eventually, the two curves, the red and the black, will cross, and this is a fully dissipative state. But is it stable? If you are here on this green point, you see that if you slightly lower the temperature, the radiated power will explode, whereas the conducted power stays the same. It cannot be stable. Right? Again, the same, if you move on the right, if you hit the plasma, the radiation falls dramatically, the conduction stays a bit the same, it isn't stable. So if the system arrives here, it will in fact jump over and fall on the stable point. That is stable because of the shape of the radiation function. Same argument as for the instability. So you see that if you want to reach this very cold plasma, you will eventually cross this unstable region and triggers a bifurcation. Let's call it a bifurcation. Okay. So that's a very simple principle of how to get something showing a transition in the divertor. Now I want to make a small 2-3 slides on a side application of it. I'm leaving the divertor, I'm showing results from West operation. Okay. We were struggling in West at the beginning because we could not keep a stable core plasma for more than 5-6 seconds. We eventually found that we were facing a transition to cold plasma in the core that was very short, leading to disruption, and we could not maintain the plasma. We worked on a model for the core volume, okay, where we assume we have some heating, and the heating of the core is then dissipated by radiation from tungsten, for instance, or from outward transport towards the plasma edge. Okay, so you balance these three equations, these three contribution to explain the core confinement. So a simple way to see this in simple dimensionless power balance is we assume that the time derivation of the time dynamic of the temperature is given by heating term minus a radiation term minus the transport. Okay, and to seek for some stability, I have explicited the temperature dependence of these different terms. The heating can be nonlinear. If you get alpha heating by fusion, it is obviously nonlinear. But if you use also lower hybrid, heating is dependent on the local temperature. So you could have some nonlinearities on the heating. The radiation is obviously nonlinear in temperature, as I showed. I'm showing here, for instance, the cooling function of tungsten. It is peaked around 1.5 keV, okay, 1,500 eV. And so this beta is positive on the left part of the peak and negative on the right part of the peak. Okay, and transport is the same. You could assume, for instance, if you make a gyrobomb model, you have a certain temperature dependence of the transport. Alpha could be 2.5 for gyrobomb transport, for instance. Okay? And so so in general, there are stable, or there are, let's say, solutions of this equation that are not trivial to find, but you can find them, and then you can perturb this solution and find if they are unstable or stable. And it turns out that there is the same simple stability criterion on these parameters. Here you can read it as beta has to be greater than something depending on alpha and gamma and the radiated fraction of the solution. So I'm not going to describe this, useless, but imagine, for instance, that you neglect the nonlinearity of the heating. So you are just looking at the radiation versus transport, which is a simple case. The stability reads as beta should be greater than alpha times a function of the radiated fraction. So if beta is positive, but this term is always negative. You see, it's F rad, so it's the radiated fraction is below 1, so this term is negative. So if beta is positive, so if you're on this left part of the radiation branch, the system is always stable. Now, if beta is negative, so if we are on this red right side of the cooling curve, the stability can be rewritten as a condition on the radiative fraction. And this radiative fraction has to be smaller than a certain value for the system to be stable. It means that if you have very little amount of tungsten in the plasma, of course, it will stay stable because the radiative fraction will be small. So you can also understand it that the radiative regime is stabilized by transports, only if transport accounts for a minimum power fraction in the system. Okay. So you can solve this equation numerically, and I'm showing here two cases. Okay. The blue one start at a given radiative fraction of 60% and high temperature. So you see here on this graph, I will start with this graph. So this middle graph shows function of electron temperature and function of central radiative fraction if the system is stable or not. So if you have a low radiative fraction, you are stable. And if you move up, you fall on the curve that is defined by the cooling function of the tungsten, and you can cross an unstable boundary, and the system becomes unstable. But what's the dynamic of this instability? This is what I'm showing here. So I have two cases. One that is hot, about 3 keV to start with, and one that is colder at 2 keV. And they have both the same tungsten concentration, same radiative fraction in the core. And you let them evolve. And if you let them evolve there, nothing happens because it's a solution of the system. But so I put a very tiny tungsten concentration increase by a few percent to force the system to radiate slightly more from the equilibrium core. What you see is that the red curve is there, it goes a bit up, it stays constant, nothing happens. It's a stable situation. Now the blue one there, it starts to increase radiation because the temperature drops a bit, cooling function makes radiation to increase, and eventually you cross the boundary and you get a very fast transition into a highly radiative regime and it falls back there in a stable position, highly radiated. And you see the typical shape of the radiation, it goes tremendously up on a few confinement time and then it stabilizes to high radiation and cold plasma. Well, we found exactly the same trend in West experiment. I'm showing here on the left time traces of central temperature. You see it's around 3 keV, it slowly drops, and eventually it falls within a few tens of milliseconds to a low temperature. At the same time, the central radiation increases dramatically, spike, and then goes down. And if you plot this time traces on the stability diagram, this is what you get. So the blue and the red are just different assumptions on how you calculate the central radiation, but they just show similar things. You start from a stable point, you cross the instability regime, you have spike of radiation, and you fall there on a highly radiative and cold central temperature plasma, as the model does. So at least it's a model that is simple, but that is able to be used to explain what we find in experiment. Okay, I want to say that this was in fact better reproduced with what we call integrated modeling, where you put a lot of physics more in this model, and it showed that the destabilization is not due to the transport nonlinearity, but by the heating nonlinearity. But it is quite similar in the phenomenology. Okay, so now I'm coming back to the problem here, that is edge dissipation. Okay, so the first experimental observation of this bifurcation to a dense and cold plasma was reported in C mode. This was one of the most famous results presented by Bruce Lipschulz, where they had this limited plasma touching the inner side of the chamber, and eventually they could find that there is a very cold and very dense plasma cloud appearing there at the contact point of the plasma with the inner wall. Okay, it is, so they called it a MARF. The acronym, I lost track of it, but it's called a MARF. It is an axisymmetric, strongly radiating belt of short radial and toroidal extent. Okay, it's dense, it's cold, and it is in pressure balance with the rest of the flux surface for stability. And it appears quickly in time. Okay, for reasons I explained before. Now, what is reported in this paper is that it can further destabilize into another state that was called at that time detached case. that's when this localized emission cloud now fills the entire flux surface, and you get a uniform emissive ring on the flux surface. And this means in that case that the plasma doesn't touch anymore the surface, radiating all over before touching the wood. And in fact, this fully detached plasma were in fact not so stable, so it was a bit of concern at that time. So an example here of a MARF observed in West this year. This is a circular plasma, and we always get it when we initiate the plasma in the chamber. The plasma is touching the inner wall, and you have here two examples of a visible image taken of this plasma. On the left, it's a low density, so 1.5 10 to the 19 per cubic meter, 400 EV at the plasma center, and the plasma at the contact with the inner wall is about 15 EV. So there is a bit of erosion, a bit of radiation. So we increase the density to 3.5, and you find that now the core temperature has increased to 500 EV, and the edge, you see, shows a very strongly radiating belt or a ring or something close to the wall. The temperature there is below 3 EV. There is no tungsten erosion. There is less radiation in the core. That's why you get hotter plasma. Okay, just an illustration that even 40 years later, we still get it. But if you push further the density, you get something else. Oh, this image is really bad there. You should maybe rather look at the video. So if you push even further the density, made from Torsupra, you get this uniform radiation belt appearing in the confined region, in the confined plasma. Uniform, and the plasma stays there. It is stable, but you can stabilize it. And we look at it with a fast visible imaging camera, and you see within this emissive ring, you see filaments of light that are moving. That's a transport manifestation. These filaments, these blobs that Fulvio spoke about, you can even get them in the confinement. On this video, you should see most recent video of this situation, maybe on the screen. So it gets much more developed turbulence than on the old picture because the camera is more recent. And you get also some MHD activity because it was an unstable situation. But okay. Now, what is interesting with these plasmas, that if you look at the pressure balance, pressure profile, the red one would be a standard ohmic situation, sitting and touching the wall. The low pressure at the edge and the pressure increase over the profile. And the blue profile is this fully detached situation. The emissive ring there is about minor radius half, okay? And you see that the pressure has strongly dropped outside of this ring because the power is radiated in the ring from the core to the edge. So there is no pressure left at the edge. It is detached, not touching the wall, but within the visible, within the emissive ring and inside, you see this gradient of pressure is much steeper than on the standard case. Okay? So you have an improved confinement inside the emissive ring in this situation. And still, what is strange that you see turbulence in the emissive ring. Huh? So there is developed turbulence there, maybe at the foot of the profile, but still you get improved confinement inside, which is to me still puzzling, but it's an observation. And you get this observation also on stellarators or LHD, for instance, where they have this strange divertor MARF with improved confinement inside. Okay. So one thing that we never manage to put additional heating on this fully detached plasma. These are ohmic cases, so it's self-sustained by the current and the collisions by Joule heating inside. And when we want to add radio frequency heating, we would lose this detached phase. We never manage to keep it alive with additional heating. So we managed to do other things on Torsupra. So you have there a radiation map of a plasma. So imagine a circular plasma lying on this bottom divertor made of carbon. Okay. So the standard radiation map with carbon is that you get radiation there locally because carbon is eroded. It emits locally 20% of the input power, standard case. Now, what we did there is to increase the density with 4 megawatt of heating power. And the system eventually transits into this MARF regime appearing here. So much stronger radiation there, still localized above the limiter dominated by carbon radiation. The plasma density here is about what we call the Greenwald limit. Yes, the Greenwald fraction was 1.2. It's a very interesting scenario. Even so, it was a limiter plasma, limiter configuration in low confinement mode, we could achieve very strong density. Now, if you look at the core profile, you see that the temperature were basically the same before and after the bifurcation to the MARF regime. But the density was higher in the core. You have here the profile of the density from the center at 0, at 1 it's separatrix. You see this MARF sits at around 0.8. And you see that the density profile is steeper inside of this radiating layer. We get higher density in the core. So improved confinement again with this dissipative regime. We had a chance also to use a fast camera in this emissive cloud. And so you have here a profile along the limiter function of time of the radiation measured by the fast camera. And you see stripes there. In fact, the system shows some oscillation around 15 Hertz. We never really understood it, but it is there. Okay. So now let's go to the real situation in tokamaks with divertor. So this so-called MARF also appears in divertor, and it sits somewhere where it can live. In fact, we find that it goes just above the X point in this very expanded magnetic area. It's like so you have a sort of nozzle effect that keeps the MARF there, prevents it to move too much around. So it sits there. This is an image of the radiation taken at JET in the 90s, Guy Matthews. At that time, it was found that the confinement in the core was degraded in this situation because, not because, but it was also correlated with a strong core dilution with the low Z ions you needed to inject. So nitrogen or even carbon was enough to get there. But you found that there was so much carbon or nitrogen in the core, and the dilution was not considered compatible for ITER at that time. Okay. Now, this is a more recent image from ASDEX upgrade. Same phenomenology, you get a very strong radiation there above the X point. Here, the confinement is preserved, but you have to keep in mind that ASDEX is a heavily heated plasma compared to what ITER will be. There is still a strong core dilution with the impurities that was injected, nitrogen. But still, they consider it is ITER compatible. My opinion is that it has to be discussed again, because this core dilution is something very important when you consider the fusion power that is produced in the core. But we let the problem open. People assume ITER will be big enough so that impurities will not go in the core. It's a belief. It's a belief. Okay. So now I will speak about West, finally. Okay. So we started this MARF experiment, say 2 years ago. So what we do is that we inject nitrogen somewhere. So you see, so it's a camera looking at the plasma from the side. You have, I'm showing here the separatrix in red. The blue would be the wall contour. You see around, and so we inject nitrogen from a location seen by the camera. It makes this bright spot. And what you would see there at the bottom is that the radiation starts increasing on the high field side leg of the divertor. It grows, and eventually transits into a radiation ring sitting just inside the separatrix, kind of above the X point. Not very clear from the picture, you will get it better later. Now, if I compare the target profiles of different things, we see, so temperature is about 20 eV before sealing, or standard attached divertor, hot divertor touching the target, 20 eV on the 2 strike points there and there. Particle flux has some value, and we see also here the tungsten erosion measured by spectroscopy. The red curve, it's there. We have erosion of tungsten. So when we look into the situation where we have this MARF, temperature of the target is below 3 eV. Particle flux is still the same. So we still have particles plasma particles reaching the divertor. It's not like we completely suppressed the boundary plasma. Still there, but it is very cold and so very dense to keep the same particle flux. But the interesting point is that tungsten erosion has dropped by a factor of 10 on the divertor. So we killed the erosion. So for us, it's a very interesting scenario to operate west to reduce erosion and contamination. It's not only a nice physical situation to study. Now let's look at the more precise dynamic. So I'm showing here time traces of different quantities taken from the divertor. Okay. So we consider 2 points, one at the what we call outer strike point, and the similar one at the inner strike point in blue. What happens when we start injecting nitrogen in our stable plasma? The first thing we see is that the inner leg starts to cool down, as was shown in the camera, but the inner leg starts to radiate before the other one. And so we have a continuous decrease of the temperature there. Okay. The density rises slowly, so the blue curve rises slowly, but not much. And you see at the outer leg, nothing happens. It's same 20 eV. And eventually, there is this bifurcation into the morph. The outer leg cools immediately within 1 millisecond. Goodness. And both legs now fall in this cold regime of 3 eV. And when this transition occurs, you see the density on the 2 legs increasing tremendously. Okay? Because the pressure is almost conserved there. We have cooled the plasma, but we have maintained a flux of particles. So we are not really having a situation where we dissipate a lot of power. And a way to see this, to quantify this dissipation is to calculate what we call a degree of detachment. So you could see it as taking the flux arriving at the divertor and comparing it to what you had previously before seeding. You see that so before when seeding starts and the inner leg cools down, the degree of detachment is on 1. So at 1 meaning there is no dissipation. And at the transition, both legs start to show strong detachment. The degree of detachment goes from 1 up to 10. And eventually we inject too much nitrogen and we get a disruption. The plasma could not sustain this prediction. So this morph appearance is in fact the onset of dissipation on West. That's only when we get into this morph, then we start dissipating power and we start reducing tremendously the power load to the divertor. But we have to maintain this degree of detachment within 2 boundaries to avoid disruption. Okay. So I will try not to get a qualitative picture of what's going on there at the morph formation. So I'm showing again here the time trace of the temperature on the 2 legs. Okay, continuous cooling of the inner leg, abrupt cooling of the outer leg at the bifurcation into morph. And I'm showing here time trace of 2 density measurements. One in the core, which is stable. Okay, I will not speak about it. And one measured along a laser. So it's an interferometry measurement. We measure a line integrated density through the X point. And what we see is that at first, nothing happens. But when the inner leg has sufficiently cooled, there is a strong increase of this interferometry measurement, of the density measurement. It corresponds to a situation where you have this radiation ring appearing on the inner side. So you can associate it also to a dense and cold plasma radiating there, measured by this interferometry. At the bifurcation, the signal drops for some reason, but we interpret it as this density filament jumped inside the separatrix and comes and sits there above the X point. That's the morph, the X point radiator morph. Okay. And if you continue to sit there, this guy will increase in size, in amplitude. And it corresponds to this increase of the density measurement there. It increases up to a point where we get a disruption because this morph became too big and we lost the power balance somehow locally. Okay. Just a bit of advertisement in the sense that this is not only a scientific subject. We try to use this morph to control interesting regimes in West. I'm showing here one of the first attempts or a good attempt to control this scenario. As I said, the interferometry system shows a good signature of the state of the divertor. The interferometry is a real-time observable in our machine. We use it to control the core density, but we can also use it to control the divertor. And we could demonstrate that we can adjust the nitrogen injection along time to maintain the diverter in the MARF regime, steady state for 15 seconds here or less. Then we can stop the seeding and the system slowly evacuate the nitrogen by the pump. And we can eventually finish the discharge with no disruption. That's nice. Okay, so we have something that works for waste. We are progressing on optimizing this control and optimizing the performance of this scenario. Now you see that the dynamic here, the gas does not stay constant. The gas we inject does not stay constant across the steady state plasma phase because the pumping is slow in waste, so things evolve. The gas flow you have to inject evolves in time, even so the plasma is in steady state. Okay, so now I come a bit on transport, theory, edge transport. So I will show here results obtained with Doppler backscattering okay, on west. So it was presented this morning. It's a radar system. It measures the perpendicular velocity of fluctuations at the plasma edge. And you can get rotation profiles across the plasma edge. Okay. So at the bottom, you see radial profile around the separatrix. So outside of it, right side of one is scrap-off layer. Inside is just inside of the confined region, what we call the pedestals. So before seeding, so in standard plasma, you take the light blue points. You have this standard situation where the rotation is positive in the scrape-off layer, meaning the flow goes down from midplane to target. So it's a standard rotation direction in west. In the scrape-off layer, it's mainly driven by the schist conditions at the target, we believe. We'll see that we have confirmation. Now, inside the confined region, the flow reverses. We have this electric field well, as it was presented for H mode in mass, but we still have it in low confinement mode in west. We have this ER well, and this negative rotation there is mostly driven by the ion pressure, ion momentum conservation and the ion pressure profile. I'm long. So when we start seeding, what we see is that we start to drop, to enhance this rotation well. It means that we are improving the confinement. We are steepening the ion pressure gradient there. And when we get into this Murphy regime, it's even getting even more intense. Okay. It shows that this MARF, or at least the nitrogen we inject into plasma, plays a strong role on the edge transport, steepening the kinetic gradients. Unfortunately, we don't measure this kinetic gradient, so I cannot tell about consistency of this picture. Now, an interesting point also, you will see in the scrape-off layer, the rotation has vanished when we are in X-point radiator region. And as I said, we have very cold targets. So it means that the schist polarization is really small, as it goes like 3 times TE. This polarization propagating in the scrape-off layer means there is no potential there, no rotation. Last point also maybe on, so we have Langmuir profile of the plasma top in the scrape-off layer. They saw no change of profile between standard situation and the Murphy situation or X-point radiator situation. In the scrape-off layer at the top, the plasma is the same, independent of what's going on at the bottom, apart from the rotation. Okay. Well, this I will skip. So we are working on a different radiation map with filters to understand what is radiating there, but I will not comment this. Now, I wanted to make a point on what we understand of this situation using direct numerical simulation with the code Solage. So to make it brief, Solage solves for a multi-species transport along field line. The perpendicular transport here is described as a simple diffusion, but we have the E cross B drift and grad B drift in it. Okay. No, the situation there is the simulations I will show are not exactly picking 100% validated against experiment. They are close to experimental conditions. I just want to see if qualitatively we can recover what we find in experiment. Okay, and the answer is yes. Okay, with drift on. When we look at the dynamic of the simulation, when we start injecting nitrogen, we see the continuous cooling of the inner leg, an abrupt cooling of the outer leg. We see an increase of the density there along this line of sight and interferometry. We see a sharp increase, drop when the morph occurs as in experiments. So it's quite convincing that the simulation is able to cope. At least the physics inside the model is able to cope with what we observe. So the 2D maps got from the simulation are shown here. So radiation map at the top, bottom shows the electron temperature map. So we start without seeding, electrons are having about 20 eV at the target, radiation very low, concentrated there at the target. Now you inject nitrogen, you wait a bit, and you get this high field side, high density, highly radiating front appearing there on the inner side of the separatrix, close to the divertor. You see the inner target has cooled below 3 eV. And you wait a few milliseconds, and this guy jumps inside the separatrix and sits there somewhere above the X point, but not really above, but inside the separatrix. And that's a stable mark. This situation is stable. And in this situation, you recover that the two targets are very cold, below 3 eV. And you don't need turbulence to get there. It's simple diffusion and E cross B and grad B drift at play. If you look into this morph, the profile of density and temperature, you find that indeed around it's hot, let's say 50 eV, it drops to a few eV inside this morph, comes up, the density does the contrary. It is a certain density multiplied by about 10 in the morph and falls there. But it's a morph, this localized, dense, and cold blob, let's say. And the radiation there you get into it, it is strongly radiating. You see the radiation is not uniform in the blob. There is some asymmetry of the radiation. That's this black curve. And it's probably because you get transport effect there, but transport of impurity. So this is a bit buzzy picture, but what we did in the simulation is to extract this cooling function I talk about the impurity. I show here the black curve is this standard picked radiation efficiency of an impurity peaking at 15 eV. That's for nitrogen. That's what you get in modeling databases, assuming ionization equilibrium. And all the curves there show what we measure in experiment in the simulation, locally, around the morph. In blue, before the morph, a few milliseconds before the morph crosses the separatrix, you see it's completely out of this ionization equilibrium. And for me, having very strong radiation at 60 eV means that you basically moved ions in a place where they would radiate a lot before getting further ionized. So it's something out of ionization equilibrium. And also, if you wait for the morph to stabilize, you get the red curves that are also very different from the ionization equilibrium states. So it shows clearly that transport of impurities there plays a very important role to understand the bifurcation dynamic and the final state of the system. And this should have, it was mentioned by Uli Strauss in his model, that it should be considered, but how much effort should be put there? It's a question of how much you want a reduced model to describe precisely your experiment. Okay, a last thing, and then I will come to the end, is the role of drift. Okay, in experiment, I showed you before stable situations with primary X point at the bottom. And it's called favorable configuration because big grad B drifts toward the main divertor. But we repeated this experiment with an active X point at the top, on a symmetric divertor located at the top. And what you see that we inject nitrogen, we see the high field side, high density filament forming, jumping across the separatrix, but instead of stabilizing into a morph at the top, the morph falls along the inner boundary of the separatrix, goes to the bottom, and then starts to come up again in the core, and we get a disruption. So it shows that the direction of the magnetic field with respect to the active X point plays an important role in the stabilization of the X point radiator. Not on the dynamic to get there, not on the onset, but on the stabilization. So we repeated that by Solej. Thank you, Hao, for doing so. Here we did simply repeat the simulation by reversing B. So it's a similarity experiment, if you want. And what we find the same, we get a high field side, high density front forming, crossing the separatrix, and the staff moves up along the separatrix on the inner side and then propagates inward, like an experiment. Shows the role of B grad B drift on the system, or E cross B drift, because it will reverse. So, yeah. Just to say that Solej is not the only code getting there. SolPS demonstrated already steady state situations that resemble experiment. And what could be most interesting here is grid simulations. That is a 3D full turbulence resolution where they did impurity scan and we could develop something that resembled this morph with turbulence. I cannot say more about how much turbulence is important or how much turbulence is impacted by this morph at that stage. Just still what they found is that there is indeed a inward transport there at the separatrix when the morph forms. So to conclude, something that was discussed maybe previously, that so this morph sits there above the X point on a very localized area. If you map this area on flux surfaces to the midplane, the extent here is just 1 millimeter. It's very tiny because the flux expansion is so strong here. So the question on how much this radiation can impact profile at the top on this very layer has to be understood, not clear to me. It sits also in a region where the magnetic shear and flux expansion will any or destroy any vortices created at the midplane expanding along field lines. Okay, so there is probably little impact of this X-point radiator on turbulence. Of course, in the scrape-off layer, I mean, there, as I showed, we get dense and cold plasma. So in the scrape-off layer, maybe this local resistivity, enhanced resistivity, could have an impact on the filamentary transport, as Fulvio described this morning. We don't know. But as I said, something clear from Solej at least is that the transport of impurity is an important ingredient on the situation. And as I said, also drifts are important, but these are not really turbulent. Transport is most toroidally symmetric drifts. And that's it. Thank you.